Hello friends, welcome to my lecture on representation of graphs. Although a diagrammatic representation of a graph is very convenient for a visual study, but this is only possible when the number of nodes and edges is reasonably small. Now, there are two types of representations: matrix representation. Okay, let us consider the matrix representation. The matrices are commonly used to represent graphs for computer processing. The advantages of representing the graph in matrix form lies in the fact that many results of matrix algebra can be readily applied to study the structure properties of graphs from an algebraic point of view. There are number of matrices which one can associate with any graph. Let us discuss the adjacency matrix and the incidence matrix. Let us first discuss adjacency matrix, representation of an undirected graph. Suppose we want to represent an undirected graph, then the adjacency matrix of an undirected graph G with n vertices and no parallel edges. Okay. So, is an n by n matrix A equal to Aij, where elements are given by Aij equal to 1 if there is an edge between ith and jth vertices, and 0 if there is no edge between them. So, when we consider the case of an undirected graph where there are n vertices and no parallel edges, we will have a n by n matrix, and the ijth entry of that n by n matrix is defined as equal to 1 if there is an edge between ith and jth vertices, and 0 if there is no edge between them. Now, let us look at some observations of these adjacency matrices. We shall see that A is a symmetric matrix, Aij equal to Aj for all I and j, because if there is an edge between ith and jth vertices, then Aij will have value 1 and also Aj will have value 1, because it is an undirected graph. Now, the entries along the principal diagonal of A are zeros if and only if the graph has no self loops. So, when the graph has no, because the diagonal entries are given by A11, A22 and so on ANN. So, that means if there are no self loops, then A11, A22, A33 and so on ANN will all be zeros. So, the entries along the principal diagonal of A are zeros if and only if the graph has no self loops. Now, a self loop at the vertex corresponds to Aii equal to 1. Okay. So, if there is a self loop at the vertex, okay, it corresponds to the entry of the main principal diagonal Aii equal to 1. The vertex, you say, but the vertex is Bi. At the vertex Bi, if there is a self loop, then the corresponding, because Aii means the edge from Bi to Bi. So, if there is a self loop, then Aii will be equal to 1. Now, if the graph is simple, there is no self loop, no parallel edges, then degree of vertex equals the number of ones in the corresponding row or column of A. Okay? Because if there is no self loop or no parallel edges, then how we define the degree of a vertex? Degree of a vertex is the number of edges that are associated with that vertex, okay, that are incident on that. So, number of ones in the corresponding row or columns, because the matrix is symmetric. So, we can count the number of ones occurring in that particular row or column, it will give you the degree of that vertex. Suppose that vertex is Bi, it is associated with B1, it is associated with B2, it is associated with B5, then Bi1, Bi2, Bi5 each will carry value 1. So, number of ones in the ith row or the corresponding column, okay, will tell you the degree of the vertex of that. Now, ijth entry of A to the power m is the number of paths of length m, okay, from vertex Bi to vertex Bj. So, ijth entry of A to the power m is the number of paths of length m from vertex Bi to vertex Bj. A to the power m means A into A m times. Now, G be a graph with n vertices, let us say G be a graph with n vertices B1, B2, Bn, and let A denote the adjacency matrix of G with respect to this listing of vertices B 1, B 2, B n, and let B be the matrix B equal to A plus A square, A cube and so on A to the power n, then G is a connected graph if and only if B has no 0 entries. Now, this can be used to check whether a given graph is connected or not. So, the adjacency matrix can be used to check whether the given graph G is connected or not. Okay. So, that is one very important use of the adjacency matrices. Now, here we are taking one particular order of B 1, B 2, B n. There can be n factorial order in which these B 1, B 2 B n can be arranged. So, there is not one adjacency matrix, there are n factorial adjacency matrices corresponding to the n factorial arrangements of B 1, B 2, B n. Now, let us go to other uses of adjacency matrices. Adjacency matrices can be used to represent undirected graphs with loops and multiple edges. Here we assumed that in the that there were no loops or multiple edges, but adjacency matrices can be used to represent undirected graphs with loops and multiple edges also. A loop at the vertex B I must have the element A I equal to 1 in the adjacency matrix. When multiple edges are present, okay, the adjacency matrix is no longer a 0 1 matrix, okay, because if there are at the vertex B I you see that there are multiple edges, then the entry A I j will not be 1 or 0. Okay. So, since the I jth entry equals the number of edges that are associated between B I and B j. Okay. So, if there are multiple edges present, then the adjacency matrix will no longer be a 0 1 matrix. All undirected graphs including multigraphs and pseudographs have symmetric adjacency matrices. Now, representation of a directed graph. The adjacency matrix of a direct digraph, okay, directed graph, or we can call it a digraph with n vertices is the matrix A equal to A I j n by n, in which A I j is equal to 1 if arc B I B j is in D. Okay. So, if B I and B j are joined by an arc, then A I j will have value 1, otherwise it will have value 0. Okay. Now, let us now go to observations regarding the adjacency matrix in the case of digraph. A is not necessarily symmetric, since there may not be an edge from B I to B j, because it is a directed graph. Okay. So, suppose this is your vertex B I and here is the vertex B j. Okay. We may have the direction associated with this edge, it is from B I to B j. So, then A I j will have value 1, okay, but A j I will have value 0, because the direction is from B I to B j, not from B j to B I. As we have seen here, B I B j means the direction is from B I to B j. B I is initial point and B j is terminal point of the edge. Okay. So, the edge not necessarily symmetric, since there may not be an edge from B I to B j when there is an edge from B j to B I. So, if there is an edge from B j to B I, it could be like this also. There is an edge from B j to B I, but there is no edge from B I to B j. Now, the sum of any column of column j of A is equal to the number of arcs directed towards B j. Okay. If you take the jth column of the adjacency matrix A, okay, then the sum of the entries of the jth column gives you the number of arcs that are directed towards B j. Okay. So, this is, suppose you are B I, this is B j, okay, and then you have other vertices, say B j plus 1, B j plus 2, you have B 1, B 2. Okay. So, suppose they are joined like this, we can take multiple edges. Okay. We can take multiple edges here. So, then suppose situation is like this, B 1 to B j like this. Okay. Then bj bj plus 1, okay. bj bj plus 1 will be equal to 1, okay. And bj bj plus 1 will be equal to 1, this is say bj plus 2, okay. So, bj bj plus 2 will be we are taking a okay, we are taking column j, huh? So, b1j b2j, that we have to consider like that okay, not this, okay. We are talking about jth column, okay. So, jth column means we have to see what is b1 bj, okay. b1 bj since the direction is from bj to b1 to bj, okay. So, we have bj b1 bj equal to 0, okay. b1 bj equal to 0, okay. In the jth column b2 b1 bj equal to 1, not 0. Okay. b2 bj b2 bj equal to 0 because the it is from bj to b2, not b2 bj, okay. And then suppose it is there is this one bj, we can say this is bj plus 1 in the jth column, okay. Then bj plus 1 bj this is equal to 0, and in this situation we have bj plus 2 bj equal to 0 because bj plus 2 to bj we do not have any edge. Okay. So, now you can see suppose this is the situation for others are all zeros, okay. The situation is only like this. So, then b1 0 0 0 other entries are all zeros, okay. Then we will have sum of the entries of the jth column, sum of the entries of the jth column will be 1, okay. So, that will tell us the number of arcs directed towards bj. So, this you can see here b1 to bj is equal to 1. So, number of sum of the column of jth column of A tells us the number of arcs that are directed towards bj, because the arcs that are directed towards bj, for them the value of the Aij will be equal to 1 for I equal to 1 or I equal to 2 or I equal to 3, okay. And so, the number of if you consider the sum of the entries in the jth column, it gives us the number of arcs that are directed towards bj. Now, sum of entries in the row I is equal to the number of arcs that are directed away from the vertex bi, okay. Because here what happens is in the row ai the entries will be like this ai1, ai2, ain, okay. So, ai1 equal to 1 means what? ai1 equal to 1 means bi b1, b1 equal to 1, okay. ai1 equal to 1 means bi b1 equal to 1, and bi b1 equal to 1 means the direction from bi to b1. So, they are directed away from bi, okay. So, sum of entries in row I is equal to number of arcs directed away from the vertex bi, that is out degree of bi, okay. Here this is in degree of bj, okay. So, the ij entry of a to the power m is equal to the number of paths of length m from vertex bi to vertex bj. The diagonal elements of A transpose show the out degree of the vertices, okay. When you consider A transpose means you multiply the elements of ith row of A by the jth column of A by the jth column of, if you have A B, B multiply ith row of A by jth column of B, okay. So, A I j becomes A ith row of A will become there ith column of B. So, we will have out degree of the vertices. I multiply ith row of A, okay. Let us see, we have ith row ai1, ai2, if you find the ijth element of ijth element of A transpose, ijth entry of A transpose equal to ith row of A multiplied by ith row of A into jth multiplied by jth column of A transpose. Okay. So, ith row of A will give you diagonal elements of A transpose. Diagonal elements of A transpose means ith row okay. Diagonal elements of A transpose means ith entry. Ith entry of A transpose means ith row of A into ith column of okay, ith because we are talking about diagonal elements okay, of A transpose. So, this means ith row of A into ith column of A transpose. Ith column of A transpose means ith row of A into ith row of A. Okay. Ith entry of A transpose means ith row of A inner product of that with ith column of A transpose. Ith column of A transpose is ith row of A. Okay. So, ith row of A if it is ai1, ai2, aiN then the diagonal element ii will be becoming ai1 square plus ai2 square and so on ain square. Okay. And the sum of entries in row I is equal to sum of arcs directed away from the vertex bi. So, diagonal element show the out degree of the vertices. Okay. Ijth entry will be equal to ai1 square plus ai2 square and so on ain square. Okay. Now, either the value of these are ones or they are zeros. Okay. So, see we have diagonal elements of A transpose the out degree of the vertices because ith entry of that is ith entry of A transpose is ith row of A into ith column of A transpose, which is ith row of A into ith row of A. Okay. So, ith row of A is ai1, ai2, ain. Okay. And when you multiply ai1, ai2, ai1 and this row by the column ai1, ai2, ain. Okay. What we get is ai1 square plus ai2 square and so on ain square. And ai1 means what? ai1 means bi b1. Okay. bi b1 will have value 1. Okay. If bi vertex it will have value 1 if that the edge is directed from bi towards b1. Okay. And bi b2 similarly will be equal to 0 if bi is directed when bi when b2 is directed towards bi. Okay. So, then it will be 0. So, what will happen if it is 1 it is 0 and so on it is 1. So, the sum of these ones they will tell us the out degree of bi because either the value of aij equal to 0, aij equal to 0 or aij equal to 1. So, diagonal elements tell us the out degree of the vertices. Similarly, diagonal entries of A transpose A tell us the in degree of the vertices. Now, the adjacency matrices can also be used to present directed multigraph. Such matrices are not 0 1 matrices when there are multiple edges in the same direction connecting the two vertices. So, such matrices cannot be 0 1 matrices. In the adjacency matrix, for a directed multigraph, Aij equals the number of edges that are associated with Bij. So, if there are multiple edges, then Aij will equal to the number of edges that are associated to Bj. Now, let us see let us use adjacency matrix to represent the graph shown in this figure. Okay. So, here we can see we have 4 vertices B1, B2, B3, B4. Okay. So, we will have n by n matrix, that is 4 by 4 matrix here. Now, there is no self loop at B1. So, B1 is so A11 is equal to 0. Okay. A12. Okay. Now, A12 B1 is connected to B2. Okay. There is a edge between B1 and B2. So, B1 B2 A12 is equal to 1, then B1 B3. Okay. B1 B3 are joined. So, A13 is equal to 1, then B1 B4, that is also there is an edge between B1 and B4. So, this is equal to 1, B2 B1 is also equal to 1, and moreover this matrix is symmetric. So, first row will be same as first column. So, we can write like this, and then B2 there is no self loop at B2. So, we have B2 0. So, B2 B3 joined to B3. So, we have 1, B2 B4 there is no edge between B2 and B4. So, we get 0, and then B3 okay. So, 1 0 1 0. So, we have 1 0 1 0. Now, we consider B3 there is no self loop at B3. So, we get 0. B3 B4 is 1 because B3 is joined to B4 by an edge, and then B4. Okay. So, we have 1 1 0 1 1 1 0 1. Okay. Now, B4 at B4 there is no self loop. So, we get the value 0. So, for this adjacency matrix is this. Okay. And in this case part 2, let us find the adjacency matrix for part 2. So, here A will be equal to, now we have 3 vertices B1, B2, B3, B1, B2, B3. Okay. So, at B1 there is no self loop. So, we get 0, and then B1 is joined to B2. So, we have value 1, B1 is not joined to B3 by an edge. So, we get 0, and then we have this symmetric matrix. So, 0 1 0. Okay. So, there is a self loop. So, let us see B2 B1 B2 is joined to B1. So, we get 1 here, and then B2 at B2 there is a self loop. So, we get value 1. Okay. So, it is not a symmetric matrix, you can see, and then B2 is joined to B3. So, we get B2 joined to, and there are multiple edge between B2 and B3, this and this. Okay. So, B2 B3 equal to 2. Okay. Now, B3 B1 okay, 0, and then B3 B2 equal to 2, and then B3 B3 is 0. Okay. So, this is the adjacency matrix for this problem. Here it is not symmetric because in this graph there are multiple edges and self loop. Okay. There is one self loop and we have 2 multiple edges. Okay. Now, in the part C, so this is part B. In the part C we have 4 vertices. Okay. So, B1, B2, B3, B4, and we have B1, B2, B3, B4. Now, let us see what is the matrix. Okay. So, B1, at B1 there is no self loop. So, we get 0, B1 is joined to B2. So, we get value 1, B1 is joined to B3. So, we get value 1, B1 is joined to B4, we get value 1, and then B2 B2 is joined to B1. Oh, sorry, it is a directed graph. So, we have to see that. Okay. So, B1 to B1 is 0. Now, B1 to B2, okay. B1 to B2 is 1, okay. Then B1 to B3 is 1, B1 to B4 is 0 because we have B4 to B1, not B1 to B4. So, B1 to B4 is 0, B2 B1, B2 B1, B2 B1 is 0, and then B2 B3, B2 B3 is also 0, B2 B3, B2 B2 is 0, okay, B2 B2 is 0 because at B2 there is no self loop, so we get 0, B2 B3, B2 B3 is 1, okay, and B2 B4, B2 B4 is 0, and then we get B3 B1, B3 B1, B3 B1 is 0, and then we get B3 B2, B3 B2 is 0, then we get B3 B3 B3, that is 0, B3 B4, B3 B4 is also 0, no, B3 B4 is 1, okay, because we have this direction, okay, and then B4 B1, B4 B1 is equal to 1, this is 1, okay. Okay, B4 B1 equal to is 1, then B4 B2, B4 B2 is 0, B4 B3, B4 B3 is 0, and B4 B4 it is 0, okay. So, these are the adjacency matrices in the case of undirected graph and directed graph. These two are undirected graphs, first A part, B part are undirected graphs, C part is a directed graph. In the part A there are no multiple edges and self loops, in the part B there are multiple edges and self loops. Okay, so, in the case of a directed graph we have to take care of the direction. Now, so this is the matrix to the part A, adjacency matrix to the part A, we can see 0 1 1 1, 0 1 1 1, 1 0 1 0, 1 0 1 0, 1 1 0 1, 1 1 0 1, 1 0 1 0, 1 0 1 0. So, that is adjacency matrix for part A, then adjacency matrix for part B, 0 1 0, okay, 1 1 2, and then 0 2 0, okay. And then we have adjacency matrix for part 3, let us see that one also. So, we have 0 1 1 0, 0 1 1 0, then 0 0 1 0, 0 0 1 0, then 0 0 0 1, okay, then 1 0 0 0, 1 0 0 0, okay. So, now let us go to incidence matrix, okay, representation of an undirected graph. First we discuss this. Consider an undirected graph G equal to GVE, okay, which has n vertices and m edges all labeled, okay. Now, the incidence matrix B equal to Bij is then n by m matrix, where Bij equal to 1 when edge Ej is incident with Bi, okay, otherwise 0. Let us make a number of observations about the incidence matrix B of G. A row with all 0 entries corresponds to an isolated vertex. If there is an isolated vertex, then no row is no edge is incident on it. So, corresponding to that isolated vertex, row will have all 0 entries. Now, a row with a single unit entry corresponds to a pendant vertex. The number of unit entries in row I, is equal to the degree of the corresponding vertex Bi, because the row Bi will contain Bi1, Bi2, Bin, okay. So, this means Bi1, Bi2, Bin, if the number of unit entries in that will tell you that the how many edges are incident on Bi, incident on Bi, okay. The number of unit entries, okay, in this row, ith row will tell us the number of edges that are incident on Bi. So, it will tell us the degree of the vertex Bi. The permutation of any two rows or any two columns of B corresponds to a re-leveling of the vertices of G. Now, two graphs are isomorphic if and only if their corresponding incidence matrices differ by a permutation of rows and columns. If G is connected with n vertices, then the rank of rank of B is equal to n minus 1. Now, let us see incidence matrices can also be used to represent multiple edges and loops. Okay. Multiple edges are represented in the incidence matrix using columns with identical entries, since these edges are identical with the same pair of vertices. Loops are represented using a column with exactly one entry equal to 1 corresponding to the vertex that is incident with this loop. Let us look at some this definition, representation of directed graph. The incidence matrix B equal to Bij of digraph with n vertices and m edges is n by m matrix, in which Bij equal to 1 if arc j is directed away from a vertex Bi. Okay. So, if arc j is directed away from vertex Bi, Bij will have value 1. If arc j is directed towards vertex Bi, Bij will have value minus 1, it will have value 0 otherwise. Let us say for example, this undirected graph, this undirected graph. Okay. So, let us see for the for this graph we have the matrix incidence matrix I. So, we have just a minute. Okay. We have the incidence matrix I, we have E1, E2, E3, there are 5 edges E1, E2, E3, E4, E5, and there are 4 vertices one V1, V2, V3, V4. So, let us see, we will have n by m matrix. Okay. N is the number of vertices. So, 4 by 5 matrix, n is the number of vertices, 5 is the number of edges. Okay. So, let us see how we defined because we are dealing with undirected graphs, Bij equal to 1 when edge Ej is incident with Bi. So, let us see E1 is incident with the vertex B1. So, we will have this B11 equal to 1. Okay. Then E2 is not incident on B1. So, we have 0. E3 is not incident on B1, E3 is not incident on B1. So, we will get value 0. E4 is incident on B1, you can see this E4, it is incident on B1. So, we get value 1. E5 is incident again on B1, okay. This E5, this is incident on B1. So, we will get 1. B2 is E1 is incident on B2, okay. E1 is incident on B2. So, we will get value 1. E2 is incident on B2, so we will get value 1. E3 is incident on B2, no, E3 is incident on B2, E3 is here, it is not incident on B2. So, we will get value 0, and E4 is not incident on B2. So, it is 0. E5 is not incident on B2. So, we will get 0. Then E1, is it incident on B3? No, E1 is not incident on B3. E2 is incident on B3, E2 is incident on B3, yes, E2 is here, B3 is here. So, it is incident on B3. So, we will get value 1. E3 is incident on B3, yes, E3 is here and B3 is here. So, we get 1 here. Then E4 is incident on B3, E4 incident on B3, no. Then E5 incident on B3, E5 incident on B3. So, we get 1. Then E1 is incident on B4, E1 is not incident on B4. Okay. So, we get 0. E2 is incident on B4, E2 is incident on B4, no. E3 is incident on B4, E3 is incident on, yeah. So, we have 1 here, E3 is incident on B4, and E4 is incident on B4, yes, it is incident on B4. So, we get 1 here, and then E5, is it incident on B4? No. So, we get 0 here. So, this is incidence matrix for this undirected graph, and in the case of this directed graph we have I equal to, okay. So, we will have how many vertices are there? 1, 2, 3, 4, okay. So, B1, B2, B3, B4, and the edges are E1, E2, E3, E4 and E5, okay. So, again 4 by 5 matrix we will have. Okay. Now, let us see how we define for a directed graph the incidence matrix. Bij equal to 1 if arc j is directed away from vertex bi. Okay. So, let us see, and if it is directed towards, we put minus 1. So, here E1 is it directed towards or directed away? E1 is directed away from B1, okay, and when it is directed away from B1 we put 1. So, B1 E1 is directed away from B1, so we put 1 here. E2 is directed E2 B1, okay, there is E2 is here, okay, and B1 is here. So, there is no relation between E2 and B1. So, we put 0 here. E3 B1, E3 is here, B1 is there. So, this is also again 0. E4 directed towards B1, E4 directed towards B1, and when it is directed towards B1 we put minus 1. So, we put minus 1 here. E5 directed away from B1. So, we put 1 here, and then B2 sorry E1 is directed towards B2, okay, towards B2 means minus 1, okay. So, we put minus 1 here. E2 is directed away from B2, okay, away from B2 means plus 1, okay, plus 1, and then E3 where is E3 is here and B2 is there. So, we put 0. E4 is here, B2 is there. So, we put 0. E5 is here, B2 is there. So, this is 0, and then E1 B3 E1 is here, B3 is E1 is here, B3 is here, okay. So, 0. E2 is directed towards B3, okay, directed towards B3 means minus 1. E3 is directed away from B3. So, we put 1 here. E4 is here, B3 is there. So, we put 0. E5 B3 E5 directed towards B3, okay, towards B3 means minus 1, okay, and then B4, okay, E1 is directed B4 is here. So, this is 0. E2 is again here and B4 is there. E3 is directed towards B4. So, we get minus 1. E4 is directed away from B4. So, we get plus 1, and then E5 is here, B4 is there. So, we put 0 here, okay. So, this is how we write the incidence matrix for this directed graph, okay. So, this is the incidence matrix. This is the incidence matrix for the undirected graph. 1 0 0 1 1, okay, 1 0 0 1 1, 1 1 0 0 0, 1 1 0 0 0, we get 0 1 1 0 1, okay, and then 0 0 1 1 0, 0 0 1 1 0, okay. Then we have this for this graph. This is A part and this one is B part, and B part we have 1 0 0 minus 1 1, 1 0 0 minus 1 1, and then we have minus 1 1 0 minus 1 1 0 0 0, okay, and then 0 minus 1 1 1 0 minus 1 1 0 minus 1, and then we have 0 0 0 0 minus 1 1 0, 0 0 minus 1 1 0. So, that is how we find the incidence matrix for the case of the two graphs. One is directed, the other one is for the first A part, which is undirected graph, and for the B part, which is a directed graph. So, that is all in this lecture. Thank you very much for your attention.